Okay. So till now, in the last class, we have discussed about uh, this, if X is a topological space and X naught and X1 are points and H is a path joining X naught and X1, then this fundamental group based at this X naught, there is an isomorphism from fundamental group based at X1 and fundamental group based at X naught, right? That isomorphism was given by this beta H, this it was given by beta H of H of this class. Okay. So in particular, if so this is an isomorphism between groups, right? This and this. So if your space X is path connected, so if X is path connected, then this fundamental group based at one point will be isomorphic to fundamental group based at any other point in that space, right? Because if X is path connected, then there is a path between any 2 points, X0, X1, right? Given any 2 points, X0 and X1, fundamental group, there is a path, and hence there is a homomorphism, there is an isomorphism from here to here, right? So if you have a space X which is path connected, then fundamental group based at here and fundamental group based at here will be isomorphic. This is true for every point X and Y in capital X, right? So if X is path connected, then there is no significance of putting this base point, right? Because this is of course isomorphic to pi 1 X Y for every X Y in capital X. So in place of this, we can just talk about fundamental group of X. Okay. Next, we have following definition. A topological space X is called topological space X is called simply connected if it is path connected and it has trivial fundamental group and has trivial fundamental group. So what is trivial fundamental means? You know, is trivial group is what? Containing just one element, that is identity, right? So if space is path connected and its fundamental group is trivial, then space is called simply connected. So examples you can see that uh, if you consider just simply this disk, right? Two-dimensional disk, like this, then this is simply connected, this even Rn is simply connected, right? Even this for every n it is simply connected. And of course, if you see the annulus, right, then it is not simply connected. So if you just see this annulus, right, this is field, this is whole, right? So this is not simply connected, not simply connected. Though it is connected, but its fundamental group is not uh, trivial. We will see how, right? So see, not simply connected. Similarly, circle also, right, is not simply connected. It is connected, it is path connected, but not simply connected. But this is simply connected. Simply connected. So we will see that how this fundamental group of this kind of space is uh, not trivial. In fact, fundamental group of this will be Z, right? So X is there, then pi 1 X be Z. Next, we have a result. This proposition a space X is simply connected if and only if there is a unique homotopy class topy class of paths connecting any 2 points, right? So proof. So if we have a space, right, then this space is simply connected if and only if given any 2 points, there is a unique homotopy class of paths connecting these 2 points, right? Uh, so let us prove it. So let X be simply connected. Let X be simply connected. Right. Let us choose, let x0, x1 be any 2 points, right? We want to show that there is a unique homotopy class of paths connecting x0 and x1. So x0 and x1 are arbitrary points in X. Since X is simply connected means that it is path connected and its fundamental group is trivial. X is path connected and uh, equal to this trivial identity. Okay. Hence, there exists hence there exists a path f from I to x such that because x is simply connected and hence path connected, hence there is a path joining x naught and x1 such that f0 equal to x naught and f1 equal to x1. Now what we can do is following. We will show that given any other path, right? So it shows that there is a unique path, unique homotopy class of paths connecting. So existence is already there. So clearly there is a path joining x naught and x1, and hence of course there is a homotopy class of paths connecting x naught and x1. In particular, we can take class of f, right? Thus is a homotopy class of paths connecting x naught and x1 if G is any other homotopy class. So we want to prove uniqueness now. Homotopy class of paths between x naught, homotopy class of paths connecting x naught and x1, connecting x naught and x1. Then we have so if this is x naught, this is x1, so this is f, and suppose we have another path G, right? So we are considering path class of this G and path class of f. So we want to show that f and G are actually homotopy and hence they have same path class. So basically we will show that this is nothing but this. So if G is any other path class of paths connecting x naught and x1, then we have f star G inverse equal to, right? So G inverse will be if f is this, right? If f is this, G is this, then G inverse will be something like this. So f, this is nothing but equal to f star G inverse. So what is this f star G inverse? This is f then G inverse. It is a loop with center x naught. Okay, this is a loop. It means that and because your fundamental group of x is trivial, every loop, any two loops based at a point will be homotopic. So in particular, this will be homotopic to constant loop here, because okay, but what does it mean? It means that this hence this so what we can do, we can just multiply. So this f star g inverse, we can just multiply g class of g, then we'll have epsilon x naught class g. This implies, so of course associativity of path classes of this product of path classes is there. So if we use that, then we'll have this star g inverse star g equal to epsilon x naught star g f star. This is nothing but g inverse star g. This is, and this is what? This is simply g, and this is what? This g inverse and then uh, g inverse and then g. So this is homotopic to epsilon x1, right? So this is equal to so this implies, because this g inverse star g, this is equal to epsilon x1. Okay, so we have shown the uniqueness. So one part of the proof is done. Let us consider discuss the next converse. So suppose that uh, there is a unique homotopy class of paths connecting any two points of x. Right? So we want to prove that x is simply connected. So it says that given any 2 points, there is a unique homotopy class of paths. In particular, there is clearly, in particular, there is a given any 2 points, there is a path joining them, because if there is a path class, right? Are paths joining these points, it means there is a path joining them. Clearly, x is path connected. Now this proof is almost obvious, right? So given so for in x not belonging to x, any two by the assumption any two loops uh, with base point point x naught are homotopic, because this is the assumption that if you choose any 2 points, then there is a unique homotopic class of paths. In particular, those 2 points, if you consider the single point, right? So if this x naught, suppose this is x1, so if you choose x naught equal to x1, then we will have a unique loop joining means based at any point, sorry, unique loop class, right? So by assumption, any two loops with base point x naught are homotopic. Hence, pi 1 x equal to trivial. This completes the proof. Next, this fundamental group of circle, right? So fundamental group of circle. So there is a theorem whose proof is quite lengthy, so we will not discuss the proof right now. So we may, at some point of time, we may come back and discuss after discussing covering spaces, uh, if we get time. Uh, so because proof is quite lengthy, so right now we are not going into the proof. So theorem says that the map phi from Z to S1 sending an integer n to the my phi from Z to S1 given by phi n equal to omega n, where omega n is equal to where omega ns equal to this is a loop is a loop based at 1 0 is an isomorphism. So the map phi from Z to S1 given by this, where omega n is a loop based at 1 0, which is given by this. It is an isomorphism. So let us understand a little bit. Though I discuss already up to some extent. So if we just consider this circle, consider this circle, then for when your z is, you can see when your n, right? So phi takes n to omega n, right? And omega n is a loop based at 1 0. So this is 0.1 comma 0. Okay. So here S1, of course, S1 is basically uh, X in R2 such that so this is your S1, and this you can give the parameterization of S1, right? So each point of S1 you can write it as this cos theta sine theta, right? But theta belongs to of course R. Okay. Now so this of course this there is not a uniqueness. This it is not that every theta means every point will correspond to a unique theta. So there will be infinitely many points in R for which we'll get a single point if we use this parameterization. Anyway, so this is your circle S1, and if I take n equal to 1, right? So for example, first n equal to 0, let us take. If n equal to 0, then what is this? Cosine 0, okay, and sine 0. So cosine 0 is 1, sine 0 is 0. So it is 1 comma 0, right? Omega ns equal to 1 comma 0 if n equal to 0. It means it is just constant loop at 1 comma 0. For n equal to 1, what will you have? You have cosine 2 pi s and sine 2 pi s, right? So you can see that when you complete this um, uh, so in this 0 1, right? So when you go from 0 to 1 once, then this you will complete once one round. So this you can see, just see that for s equal to 1 upon 4, you will have what? Cosine pi upon 2 and sine pi upon 2. So what is cosine pi upon 2? It is 0, and sine pi upon 2 is 1. So this is basically this point. When your s is half, then you will have cosine pi, sine pi, and that is 0, that is -1 and 0, right? And next for 3 upon 4, you will be here. Then by when you reach 1, you will come back again here, right? Now for n equal to 2, this speed of this loop, right? Speed of traversing this will be doubled, right? So when you go from 0 to 1, you can check that you will cover it 2 times. Similarly, for n equal to 3, when you go from here to here, you will cover it 3 times, and in the anti-clockwise direction. Okay. Similarly, you can for n equal to 4, you will cover 4 times. Now, for n equal to -1, you see, your direction will change. You can check from here. So for uh, when uh, uh, when you are at uh, s equal to 1/4, so you will be cosine uh, pi cosine minus pi upon 2 and sine minus pi upon 2. So cosine minus pi upon 2 is cosine pi upon 2, and this is will be minus sine pi upon 2. So we'll have here uh, this one, right? So point 0 -1. Then we will be here for s equal to half, and then here for s equal to 3/4, and then so for n equal to -1, you will traverse the circle in this direction. N equal to -2 in this direction, but when you go from here to here, you will complete 2 rounds. So from here, you can see that, of course, you have defined, yeah. So this mapping we have defined, and anyway, so we are not going to means, prove it. So now, next we have following proposition. Let X and Y be topological spaces so we can put here path connected. Let X and Y be path connected topological spaces. Then pi 1 X cross is product space, product topological space X cross Y is uh, uh, is isomorphic to one X cross and Y. So of course, if X and Y are path connected, so we can talk just about pi 1 X and pi 1 Y. And if X and Y are path connected, then X cross Y also will be path connected. Proof. Define phi from pi 1 X cross y to phi 1 x cross phi 1 y by phi f is class so I think this assumption is not required here. So we can just put extra points. So for simplicity, I mean, we could do that, but this x naught comma y naught. Okay. So this is uh, and this is your pi 1 x naught uh, y naught. So x naught comma y naught, and this x naught across y naught by this now equal to this f1 this okay where where f uh, equal to f1. So what is this? Basically, if this is a class loop class f is here based at x naught y naught, it is it has f is a representative of this class. Okay, so it means f is a loop based at x naught y naught, right? It means f is a map from I to x cross y, right? It means f is going to have two components. Okay, such that of course f0 equal to f1 equal to your x naught y naught, but okay. So this will give you that this so f10 equal to f20, sorry, f10 equal to f11 equal to x naught, and f20 equal to f21 equal to y naught. So f1 and f1 will be a loop in x at x naught, and f2 will be a loop in y at y naught. So we'll not be able to complete the proof today. So we'll complete the proof in the next class. So we'll stop here.